This video is going to focus on formulas and some terms that are associated with formulas. First, though, we're going to review what makes up a chemical formula, specifically a compound's chemical formula, and that is that you will have atoms of two or more elements combined together. When they are combined, they will always have the same relative masses of those elements. By that I mean no matter where you go on this planet, water will always consist of two hydrogens and one oxygen, and the masses associated with those elements. We use formulas to represent both the elements that are used to make our compound as well as how many atoms of that element are needed to make a molecule of it. So the example I have here, H2O, one molecule of this contains two hydrogen atoms, one oxygen atom. So some practice for one of your homework assignments. I am pretty simple. How many atoms of oxygen are in SO3? There are 3 oxygen atoms. How many atoms of hydrogen are in HC2H3O2? Because there are hydrogens both at the beginning and in the middle, you need to add the atoms together. 1 plus 3 would give me 4. And then finally in SrNO32, how many atoms of oxygen are in this formula? NO3 you have 2 groupings of, and there are 3 oxygens in each, so 3 times 2 would give me 6 oxygens. Next up, we're going to talk about empirical formulas, and empirical is just a fancy way to describe simplest. When you are asked in math class to simplify a polynomial, that's what you would be doing with a chemical formula. You are looking to see if you can find any factor that your subscripts for all of the elements present in your compound have in common. It can't just be a couple of them, it has to be all of the elements that you have. And if they have it in common, you can divide out that common factor and simplify your formula. So for the first example, glucose, C6H12O6, all of the subscripts for carbon, hydrogen, and oxygen have a 6 in common. So if I divide each of them by 6, I get 1 carbon to 2 hydrogens to 1 oxygen, CH2O. If you have a formula that is already as simplified as you can, then its empirical formula would be itself. CH2O is also formaldehyde, and because there's 1 carbon and 1 oxygen present, you cannot simplify that further. If you have 1 atom present of any element in a chemical formula, you have its empirical formula. But you could have like a ratio of 3 to 5 where 3 and 5 do not have a common factor other than 1, and that one would not be able to be simplified further. The simplest you can have is a subscript of 1. No fractions are allowed for your subscripts. So we're going to see how you can calculate an empirical formula given some data, and typically that data is in the form of percent compositions. If you assume that you have 100 grams of your compound, you can write those percent signs strictly as grams. And because we can't compare grams of elements to one another since their atoms are not made of the same numbers of protons, neutrons, and electrons, we can convert those to moles using molar mass. Even the mole amounts may not be necessarily whole numbers. Sometimes they're close, but oftentimes they're not, and so we want to set up ratios to get our subscripts to represent integers. And we do that by dividing by the smallest number of moles. Sometimes when you do those ratios, calculate those ratios, you get fractions such as like 1.49, 1 1/2, or 2.33, 2 1/3, 1.25, 1 1/4. When that happens, we need to get rid of that fraction, and we do that by multiplying by its denominator. So 0.5 we multiply by 2, 0.33 or 0.67 we multiply by 3, 0.25, 0.74 we multiply by 4. As in math class, what you do to one you have to do to all, so even if one of your ratios does not have a fraction, if any of them do, then all of your ratios have to be multiplied by that constant. And then finally, when you get whole number ratios for all of the elements making up your compound, those represent your subscripts, and that would be your empirical formula. So we're going to do a couple of calculations with this. The first one, we're going to be finding the empirical formula of a compound with barium, sulfur, and oxygen. And you're given the percentages: 58.80% barium, 13.75% sulfur, and 27.45% oxygen. So step 1 is turning those percent signs into grams. And so 58.80% barium becomes 58.80 grams of barium. Same thing for sulfur, and the same thing for oxygen. To get from grams to moles, I need to find the elements on my periodic table, find what their molar masses are. Barium is 137.33, so it gets divided into the 58.80 grams. Sulfur is 32.06. And because oxygen is not being treated as an element, it is part of a compound, or just as an element, we need to divide it by just one oxygen mass rather than the diatomic mass, so it will just be 16. Again, that's because we are not treating oxygen, or oxygen is not acting just as an element. It is part of a compound, and we are trying to figure out how many atoms of oxygen are in our compound. When we do the division, the sig fig rules apply that we would normally use when we're going from grams to moles, when we're doing that type of conversion. It looks to me that our masses all have 4 sig figs, and our molar masses have at least 4. So we want 4 in our answers. So when we do the calculation, you should get 0.4282 for your moles of barium, 0.4289 for your moles of sulfur, and 1.716 for your moles of oxygen. So we've done steps 1 and 2, we've turned our percents into grams, and we've converted our grams into moles. Our third step is to divide by the smallest number of moles, which means divide by 0.4282 for all 3 molar amounts. And once we do that division, we see that barium is exactly 1. Dividing something by itself will give you 1 always. Sulfur will be really, really close to 1, and oxygen is really, really close to 4. So our subscripts would read Ba1, S1, O4, and since the 1s are not needed, we can just write it as BaSO4. Another example, and this one's going to involve a fraction, is 52.9% aluminum and 47.1% oxygen, and we want to calculate an empirical formula again. So step 1 is to turn those percents into grams. To make 52.9% aluminum, 52.9 grams, and then the same for oxygen. Divide by the molar masses for aluminum and oxygen as single atoms, so aluminum 26.98 from the periodic table. Again, because oxygen is a part of a compound, it's just going to be divided by the mass of one oxygen atom, 16. This time our masses have 3 sig figs, so when we do the division, we get 1.96 moles of aluminum and 2.94 moles of oxygen. Steps 1, percents to gram, and step 2, converting grams to moles, are completed. So now we're going to take our smaller number of moles, which will be aluminum, and divide that into both the moles of aluminum as well as the moles of oxygen. That gives us a ratio of 1 for aluminum, and it gives us one of about 1.5 for oxygen. And so since we did not get a whole number for oxygen, if we were going to rewrite 1.5 as a fraction, it would be 1 over 2. So we're going to multiply both the mole ratios of aluminum and oxygen by 2. That gives me a 2 to 3 ratio of aluminum to oxygen in my formula. And when I write the empirical formula, Al would have a little 2 after it, and O would have a little 3. The last section that we're going to cover in this video is another type of formula, a molecular formula. And that's the true formula, the one that you would actually find it in nature, not the bare bones skeleton simplest ratio form. Your molecular formula is always a multiple of your empirical formula. It could be the same if n was 1. It could be double the empirical formula in terms of the number of atoms present. It could be 10 times. Whatever the ratio is, it will always be a multiple of that empirical formula. We can calculate molecular formulas if we know what our empirical formula is, and we know how large our molecular formula is. So first thing we want to do is find in the question information to solve for an empirical formula or the empirical formula itself. We next want to find how much the empirical formula weighs by calculating its molar mass. And then we're going to look in our problem to find how large our actual compound is, the molar mass of the molecular formula. Sometimes you can tell from 2 and 3 what the ratio is. 12 over 6 would be times 2. But sometimes it's not so easy and we have to do a division to determine what that ratio would be. When you do that division, the larger mass, which is typically the molecular formula, is found on top, and the empirical formula mass is found on the bottom. That ratio will be very, very close to a whole number. You won't have halves or thirds or fourths. Whatever that n value is, that n is telling you how many times larger the molecular formula is compared to the empirical formula, and so you multiply all the subscripts in your empirical formula by that n to get the true molecular formula. So we have a white powder here that was analyzed and determined to have an empirical formula of P2O5. Now we're told the compound has a mass of 283.88 grams. We want to know what the compound's molecular formula is. So we have our empirical formula, P2O5. We want to find next the mass of that empirical formula by multiplying 2 times the molar mass of phosphorus and 5 times the molar mass of oxygen, which gives me a molar mass of 141.94 grams. The molar mass of the molecular formula was given to us in the problem, 283.88 grams per mole. We can kind of tell from that it's going to be twice as big, but in case you're not 100% sure, you can always divide, again, the mass of the molecular formula by the mass of the empirical formula, and that gives us a ratio really close to 2. And so if my empirical formula was P2O5, I would need to double my subscripts to get the molecular formula, P4O10. And that is the end of our formulas video.